Hi, here's Tsu-Jui from UC Santa Barbara. You can also call me Ray. Today I'm going to introduce our work, Counterfactual Vision and Language Navigation via Adversarial Path Sampling. Vision and Language Navigation, aka VLN, is a task that requires an agent to achieve the goal based on the instruction in the room. For example, the instruction is about head upstairs and walk past through the piano. So the agent should first go to the right blue point to get up the stair and do the following actions. For the VLN task, the agent aligns the linguistic semantic and the visual understanding to execute series of action and achieve the goal. We can imagine that in the future, you may ask a home robot like, hey, please go to the kitchen and take the milk in the fridge. And the robot will follow your instruction, find the kitchen, and get back your milk. Although being a practical task, because the room is usually very large and there are so many possible paths, it is difficult to collect enough instruction path pairs to train a robust agent, which we call the navigator. And this kind of data scarcity issue makes learning the optimal matching between vision and language pretty challenging. In the previous work, NeurIPS 18, they tried to expand the training set by doing data augmentation with speaker. The speaker is to back translate a path into its instruction, which is pre-trained from the original set just like a video captioner. They random sample different paths in the environment and with the speaker to estimate the instruction. Then they can combine the sample paths and their instructions as an augmented data to help train the navigator better. By this way, they can make the navigator to interact with the additional data. However, the help is pretty limited since the paths are random sample and the augmented data can be too arbitrary. In our work, we try to make the sample paths more useful or more helpful to the navigator. We propose adversarial path sampling, aka APS. APS is a recurrent action selector and then combine those views and actions as the sample path. The main concept of our idea is that APS learns to sample challenging paths that navigator cannot navigate easily, and the navigator tries to solve the path sampled from APS. At first, APS samples a path and applies the speaker to get the instruction. With the path and instruction, we train the navigator and get the training loss, which is the loss NAV here. And the loss NAV represents how difficult of the path we sample in terms of the navigator. For the navigator, it minimizes loss NAV to learn from the sample path. But for our APS, it targets on maximizing loss NAV so that it can sample more challenging paths that actually help the navigator. So there is an adversarial situation of loss NAV between the navigator and our APS. APS aims at sampling challenging paths and the navigator tries to solve the navigation task from APS. By the above adversarial training process, we collect all of the sample paths and instructions to compose as the adversarial augmented data, which can be more helpful to the navigator than just randomly sampled. Another issue of the VLN task is on-scene adaptation, which means that the trained navigator can navigate well in the scene environments, but the performance will drop a lot when under the on-scene or we say unfamiliar environments. To help this kind of issue, our APS can also support so-called pre-exploration. During pre-exploration, our APS will also sample some paths under the on-scene environment, and the paths and back-translated instructions will further optimize the navigator to make it more adaptive to the target environment. Finally, the navigator can run for each instruction in a single turn. There is a similar process for like robot vacuum. When we buy a new vacuum, it will first random walk inside our room to get familiar with the on-scene environment, and then the vacuum can clean the room successfully. The evaluation result is as here. The line in color green is for the scene environment. The line in color red is for the unseen environment. First, we can see that randomly sampled, which is the light line stops improving when using more than 60% data. It means that those augmented data are not so helpful to improve the navigator. However, for the APS sample, which is the strong line, keeps improving under both seen and unseen environment. It shows that our APS sample data actually help the navigator rather than randomly sampled. And the blue line, which is the pre-exploration process, can further help the unseen environment. Here is an example of the pre-exploration. We can see that without pre-exploration, it is very difficult to walk out of the unfamiliar bathroom. The navigator just keeps turning right and stuck inside the room. However, if we do pre-exploration, the navigator can successfully get outside and achieve the final goal. That's all about our adversarial path sampler for vision and language navigation. Here's Ray. Very thanks for all your here and the listening.